Picture an office without the quiet certainty of a printer waiting in the corner. Producing a clean copy of a computer document means relying on noisy mechanical giants that strike paper one character at a time, offer only limited typefaces, struggle with graphics, and often demand specialized operators. That was the world of computer printing in the 1960s. Computers were gaining speed, yet much of their information remained trapped behind glowing screens, punched cards, magnetic tape, and crude lines of text. The digital world could calculate, organize, and store information. Yet, it had no elegant way to place that information onto an ordinary sheet of paper. Then, one engineer studied a photocopier, considered the concentrated power of a laser, and understood that the two technologies could be joined. His name was Gary Starkweather, and his invention would eventually transform offices, publishing, banking, education, design, and the personal computer itself. Because laser printers are now so familiar, it is easy to forget how radical the idea once appeared. It was not merely a faster typewriter. It was a machine capable of turning a complete digital page, including text, illustrations, charts, symbols, and different fonts, into a permanent physical document. That possibility began with a boy in Michigan who was more interested in discovering how machines worked than in accepting them as finished objects. Gary Keith Starkweather was born on January 9, 1938, in Lansing, Michigan. He grew up as an only child in a household that was not especially technological. His father managed a dairy, and his mother had experience with accounting and household work. What Gary did possess was freedom. In the basement of the family home, he was allowed to experiment as long as he did not destroy the house. Near his neighborhood was a place where people discarded old radios, washing machines, automobile parts, and other broken equipment. For very little money, he could bring home a dead radio, open its case, remove its components, and investigate the hidden structure inside. Sometimes he received an unpleasant electrical surprise, but the experience taught him something no textbook could provide. Machines were not mysterious objects created by unreachable experts. They were systems made of understandable parts, and those parts could be rearranged into something new. He built a personal supply of components and became fascinated by electronics, mechanisms, model railroads, and the practical behavior of electricity. Merely knowing that a device worked was never enough. He wanted to understand why it had been designed in a particular way and what might happen if that design were altered. This habit of questioning would later become the foundation of his career. At Michigan State University, Starkweather studied physics. The subject appealed to him because equations could explain the behavior he had observed in mechanical and electrical devices. Physics offered a language for light, motion, energy, magnetism, and matter. During his university years, he became increasingly interested in optics, including spectroscopy, diffraction gratings, and the measurement of light. He also encountered digital computers at a time when they were still enormous, expensive, and unfamiliar to most people. Early computers did not look like the compact machines that would later sit on desks. They filled rooms and were often treated as specialized calculating instruments. Starkweather learned to program one and discovered that computing could accelerate work that had once required long hours of manual calculation. The experience suggested a powerful possibility. Optical systems and digital computers did not have to remain separate fields. A computer could control light, and light could become a tool for communicating digital information. After completing his physics degree, Starkweather moved to Rochester, New York, a center of American optical research and manufacturing. He worked briefly at Bausch and Lomb, where he gained practical experience with lens design, and he pursued a master's degree in optics at the University of Rochester. Rochester was also home to the company that had become famous for xerography, Xerox. Xerography, a word built from Greek roots meaning dry writing, had changed document reproduction by allowing copies to be made without liquid photographic chemicals. A photoconductive surface was electrically charged, exposed to light, developed with toner, and then used to transfer the resulting image to paper. Developed with toner, and then used to transfer the resulting image to paper. The process was ingenious, and Xerox was still searching for uses that extended beyond ordinary copying. Starkweather joined Xerox in 1964, entering the company at precisely the moment when lasers and digital communication were opening new technical possibilities. One Xerox project was called LDS for long-distance xerography. It was an early high-speed facsimile system. At one location, a document was scanned. Its visual information traveled through a communication line, and another machine reproduced the page at a distant location. The design used cathode ray tubes, or CRTs, to handle the optical scanning and imaging. Although it functioned, the system was expensive, complex, and difficult to improve. A customer such as a railway could use it to transmit shipping documents quickly, but the equipment was not an ideal foundation for the future. Starkweather was asked to consider ways to make the system better. Because of his graduate work in optics and holography, he understood a technology that was still new and exotic, the laser. The first working laser had appeared only a few years earlier. Lasers were not yet inexpensive components that could be placed inside consumer electronics. They were temperamental laboratory devices, often difficult to start and control, yet they offered an extraordinary advantage. A laser produced a narrow, intense, highly directed beam of light. Starkweather reasoned that a laser could replace the weaker CRT light source. If the beam could be swept rapidly across the light-sensitive surface of a xerographic machine, the system might operate far faster and with greater precision. That alone promised a useful improvement, but his thinking soon moved beyond the original assignment. Why should the machine merely reproduce a page that had first existed on paper? Why could it not print information created directly by a computer? That question marked the true birth of the laser printer. The existing copying process began with a physical original. Light reflected from that page created an image on a photoconductive drum. Starkweather realized that the original page could be eliminated. A computer could control a laser beam and instruct it where to place tiny points of light. Line after line, the laser could write an invisible electrostatic image directly onto the drum. Toner would attach to that image. Paper would receive the toner, and heat would fuse it permanently. The copier would no longer be limited to copying. It would become a digital printing engine. Every element on the page could be generated by information. Letters would be patterns of dots. Photographs could be translated into varying arrangements of dots. Diagrams, mathematical symbols, logos, and illustrations could all be produced by the same machine. From a modern perspective, the concept sounds obvious because screens and printers exchange digital pages every day. In the late 1960s, however, many computer systems treated text as fixed characters sent to mechanical printers. The idea that an entire page could be constructed as an image and painted with light was both technically difficult and conceptually ahead of its time. Starkweather's proposal did not receive universal enthusiasm. Xerox was a copier company, and its managers understood the business of reproducing existing documents. A machine that created original pages from computer data appeared commercially uncertain, threatened familiar product categories, and depended on expensive components. Some managers predicted a market too small to justify the effort. Others feared the project would divert attention from established programs. Starkweather was advised to stop pursuing it. Starkweather continued anyway. After obtaining a laser, he began assembling experimental systems under conditions that made the work feel almost unofficial. He removed the optical components from a copier and attempted to replace them with a scanning laser system. The central challenge was not simply producing a beam. The beam had to sweep across the drum with extreme speed and accuracy, switch on and off in response to digital data, and remain sharply focused throughout its journey. Each horizontal scan line had to align correctly with the next. A small optical error could distort an entire page. Starkweather used a rotating polygonal mirror, a metal wheel with several polished faces. As the polygon spun, each mirror face swept the laser beam across the photoreceptor. An electro-optical device modulated the beam, turning the stream of digital bits into flashes of light. Lenses shaped and focused the beam so that it formed a small spot on the drum. The arrangement contained the basic architecture that remains recognizable in laser printers decades later. Yet the prototype revealed a serious defect. The polygon's mirror faces were not aligned with perfect uniformity. Even tiny angular differences caused the scan lines to shift vertically, producing irregular spacing and visible errors. Manufacturing a dramatically more accurate polygon would have been extremely expensive. The project appeared to face a choice between unacceptable print quality and an unaffordable component. Starkweather searched for another approach. The solution came not from making the mechanical part perfect, but from designing optics that corrected its imperfection. He realized that a cylindrical lens could compensate for the alignment error. Such a lens bends light differently in one direction than in the other. Properly positioned, it could cause the scanning system to focus each beam path onto the same reference line, despite small variations among the polygon faces. The part cost only a few dollars, yet it solved a problem that might otherwise have required a component worth thousands. This moment captured Starkweather's style as an inventor. Rather than demand perfect materials, he understood the system deeply enough to make inexpensive parts correct one another. The laser printer was becoming real, but the political struggle inside Xerox had not ended. Starkweather wanted to move to the company's new Palo Alto Research Center in California, known as PARC. The laboratory had been established to explore the future of information and computing. Its researchers were developing technologies that would later become central to modern digital life, including personal workstations, graphical interfaces, networking, and advanced document systems. To Starkweather, PARC was the ideal environment. His managers in New York were reluctant to let the project go. At one point, he was offered a major promotion, but management authority was never the objective. He wanted to build the laser printer. Eventually, he secured permission to transfer. In 1971, he and his family moved west, carrying an invention that some people still considered unnecessary. At PARC, the idea finally entered a community capable of carrying it forward. A laser scanning mechanism alone could not create a practical computer printer. The machine also required electronics capable of receiving data at high speed, memory for holding page information, hardware for generating characters and images, and software for connecting users to the device. PARC brought together physicists, electrical engineers, computer architects, and programmers. Starkweather could focus on the optical system while colleagues developed the digital systems around it. His early device became known as SLOT, the Scanning Laser Output Terminal, and used a Xerox 7000 copier as its foundation. The copier supplied the paper path, photoreceptor, toner development, transfer mechanism, and fusing process. Starkweather's scanner supplied the digital image. The hybrid was visually ungainly, resembling laboratory equipment fastened to a dismantled office machine, but its significance lay in what it could accomplish. The printer operated at roughly 1 page per second and produced output at about 500 dots per inch, an impressive resolution for the period. Unlike line printers, it could create pages with multiple fonts, sizes, orientations, graphics, and layouts. It could print information that looked like a professionally composed document rather than a stream of computer characters. To understand the breakthrough, it helps to follow a single page through the machine. A computer first describes the page as a grid of tiny picture elements. The printer then converts that grid into a sequence of binary decisions: light or darkness, dot or blank space. A photoconductive drum receives an electrical charge. The laser beam then scans across the drum, while the digital signal switches the beam rapidly. Wherever the beam strikes, it changes the electrical condition of the surface. After many horizontal sweeps, the full page exists on the drum as an electrostatic pattern. Toner particles respond to that pattern and collect in the correct locations. A sheet of paper passes the drum and receives the toner. At the final stage, heated rollers melt and press the toner into the fibers of the paper. What began as numbers in a computer emerges seconds later as a warm, permanent document. This method separates page design from physical type. A mechanical printer requires a shaped piece of metal, a print head, or another fixed mechanism to create a character. A laser printer needs only data. Change the data, and the same machine can print a different alphabet, a larger headline, a shaded image, a circuit diagram, or a complete book page. That freedom changed the meaning of computer printing. At PARC, another important development was underway: the Alto personal computer. The Alto was not a mass-market product, but it anticipated the modern workstation. It used a bitmap display, a mouse, windows, and a graphical approach to information. A screen composed of pixels naturally demanded a printer capable of reproducing a page as pixels. Starkweather's machine was the missing partner. The Alto could help generate page images and serve the printer through a network. Digital documents created on a screen could finally appear on paper, with a close relationship between what the user saw and what the printer produced. This connection helped establish the foundation for what would later be called desktop publishing. Even after the breakthrough, the path to dependable service remained difficult. A machine that performs once in an inventor's laboratory is not yet a useful product. Starkweather described levels of technical maturity with humor. At the lowest level, a system works only when its inventor is present with a screwdriver. At the highest level, anyone can use it, and it operates consistently. He wanted the printer to reach that highest level. He and his collaborators improved the laser, modulator, polygon motor, electronics, alignment, and paper handling system. One episode revealed how far he would go to keep the experiments moving. When the laboratory containing the printer was separated by roughly 2,500 feet from the computer equipment, supplying its high-speed video data, an ordinary connection could not provide enough bandwidth. Starkweather and colleague Bob Kowalski placed optical transmitters and receivers on the roofs, using lasers, modulators, telescopes, filters, and photomultipliers to bridge the distance through open air. Heavy rain could shift the building slightly and disturb the alignment, sending them onto the roofs with walkie-talkies to retune the link. Even the tiny travel time of the light signal moved the printed image about an inch across the page. Another reminder that every successful sheet depended on precise timing. They completed a character generator in 1973 and joined it to the printer in a system called EARS, the electronic array raster scanner. EARS became a network printer used throughout PARC. Employees sent documents from Alto computers and collected the pages from output bins. The system even sorted output alphabetically, so users could locate their jobs more easily. Over roughly a year and a half, it produced millions of impressions. That volume mattered because it demonstrated more than technical possibility. It proved that people wanted networked digital printing once it became available. The printer changed behavior throughout the laboratory. Researchers no longer treated computer output as crude evidence produced by a machine. They produced memoranda, reports, illustrations, manuals, and sophisticated documents. The quality encouraged them to design pages more carefully. Printing became part of the creative process. The team continued improving the system, leading to machines such as Dover, a prototype that helped point toward commercial production. The prototypes could print about 60 pages per minute at 500 dots per inch, while the eventual Xerox 9700 commercial system would reach approximately 120 pages per minute. Those figures represented a remarkable combination of speed and quality. A mechanical printer might be fast when producing simple characters, but it could not offer the same freedom of page composition. A high-quality typesetting process could create beautiful pages, but it could not respond instantly to changing computer data. The laser printer joined these worlds, combining automated speed with the flexibility of digital imaging. Technical success did not settle the commercial question. Xerox still had to decide whether the invention belonged in the market. Early estimates suggested that only a few hundred machines might be needed. The device remained large and costly, while personal computing had not yet become a broad commercial reality. The first major market was therefore not the individual desk, but the data center. Banks, insurance companies, manufacturers, and government organizations produced enormous quantities of statements, invoices, manuals, and reports. They needed speed, reliability, and the ability to change information electronically. The Xerox 9700, announced in 1977, was designed for this environment. It was based on the powerful paper handling technology of a high-volume Xerox copier and could print 2 pages every second on ordinary cut sheets. Cut sheet operation was important. Competing computer printers often used continuous fan-fold paper with perforated edges, giving documents the unmistakable appearance of raw computer output. The 9700 could produce separate pages that looked like normal office documents. It could collate them, handle multiple paper sources, and support complex layouts. A bank could generate customer statements. A manufacturer could revise a service manual in a computer file and print an updated version immediately. An organization could combine variable information with fixed forms without storing warehouses of pre-printed paper. A carefully designed business model proved almost as important as the engineering. Customers could rent the machine under an arrangement that included a very large number of pages. Once installed, the printer encouraged organizations to move more documents into digital workflows. The result was a runaway success. Tens of thousands of machines were ultimately sold, and the technology generated billions of dollars for Xerox. Some installations operated around the clock, producing vast numbers of pages. What had once been dismissed as a machine without a market became one of the most profitable technologies associated with PARC. The success also revealed an important truth about innovation. A market survey can measure what customers already understand, but it often struggles to measure demand for a capability they have never experienced. Before high-quality digital printing existed, office workers could not easily describe how they would use it. Once the technology appeared, new applications multiplied. Rather than merely serving a known market, the printer helped create one. Xerox was not alone for long. IBM introduced the 3800, a high-speed laser printing system for data centers, shortly before the Xerox 9700 reached the market. Canon developed compact laser printing engines, and Hewlett-Packard later combined Canon mechanisms with its own electronics and software to produce the laserjet. As semiconductor memory became cheaper, processors became faster, laser diodes replaced large gas lasers, and compact optical components improved. Laser printers moved from industrial rooms into offices and eventually toward individual desks. Software supplied the next decisive step. Page description languages such as Adobe PostScript allowed computers to describe text and graphics in a device-independent form. Apple's LaserWriter, introduced in the mid-1980s, connected high-quality laser printing with the Macintosh graphical environment and helped ignite desktop publishing. Small design studios, businesses, schools, and individuals gained capabilities that had once required professional typesetting equipment. Starkweather did not personally design every machine that followed, but the architecture he pioneered made the wider industry possible. The rotating polygon, modulated beam, photoconductive drum, toner development, and digitally composed page became a durable technological family. The invention also revealed a deeper convergence. The copier was an analog imaging machine, while the computer was a digital information machine. Starkweather combined them by recognizing that light could translate between their worlds. His laser did not care whether the page contained a letter, a photograph, a map, or a mathematical equation. It responded to bits, and those bits became visible marks. That principle now appears throughout modern technology. Information can be separated from the physical mechanism that presents it. The same data can be displayed on a screen, projected on a wall, printed on paper, or transmitted across a network. The laser printer was one of the machines that made this separation tangible to ordinary users. Black and white printing did not mark the end of Starkweather's career. He remained fascinated by the way computers represent visual information. In 1988, he joined Apple Computer, where he worked on publishing and color standards. Color brought a new and difficult problem. A digital image did not look identical on every monitor, scanner, camera, and printer. Each device had its own characteristics. A red displayed by one screen might appear orange on another. A photograph scanned under one set of conditions might print too dark or with an unwanted color cast. For digital publishing to become reliable, computers needed a method for describing and correcting these differences. Starkweather helped develop Apple's ColorSync system, which used device profiles and color management techniques to make visual results more consistent across equipment. The work extended the same mission that had driven the laser printer: preserve the meaning of digital information as it moves into a physical or visible form. He also contributed to film imaging and scanning. Work connected with Lucasfilm and later Pixar helped advance the digital handling of motion picture color. In 1994, he shared a scientific and engineering award from the Academy of Motion Picture Arts and Sciences for pioneering film scanning technology. The inventor, who had once used a laser to draw documents on a copier drum, had helped build tools for moving cinematic images between film and computers. In 1997, Starkweather joined Microsoft, first working as an architect in color management, and later becoming a founding member of a hardware research group within Microsoft Research. At Microsoft, he returned to the experimental environment he loved. Colleagues remembered optical benches, lasers, display components, and prototypes filling the laboratory. He encouraged engineers to test ideas quickly, learn from failure, and build physical systems, rather than allowing promising concepts to remain diagrams. His projects ranged beyond printing to large displays, projection systems, digital photography, microelectromechanical devices, and new forms of interaction. One notable experiment combined multiple projectors with a curved surface to create an extremely wide desktop display. More than a larger monitor, it invited researchers to reconsider how much visual space a computer user might need and how that space could influence productivity. Once again, Starkweather preferred to construct something that allowed people to experience the future rather than merely discuss it. Although he retired in 2005, he continued returning to Microsoft as a researcher emeritus. Engineers sought his advice because he combined theoretical understanding with the memory of countless practical failures and solutions. He knew that invention was rarely a single flash of inspiration. The celebrated idea is often only the beginning. A working technology requires alignment, calibration, materials, control systems, manufacturing, software maintenance, economics, and cooperation. Starkweather was celebrated as an individual inventor, but he also acknowledged the importance of teams. At PARC, specialists in computing and electronics helped turn his optical scanner into a networked printer. Product engineers transformed prototypes into the 9700. Later, companies reduced the size and cost. Software developers created page description systems. The larger revolution emerged from the interaction of all these contributions. Yet the initiating vision remained unmistakably his: use a controlled laser beam to write a computer-generated page onto a xerographic surface. Recognition arrived over the years. He received major honors in optics and display technology, was elected to the United States National Academy of Engineering in 2004, and entered the National Inventors Hall of Fame in 2012. These honors recognize both the commercial importance of laser printing and the originality of applying optical science to computing. Gary Starkweather died on December 26, 2019, at the age of 81. By then, the world shaped by his invention had become almost invisible through familiarity. Laser printers were producing contracts, medical records, shipping labels, textbooks, court documents, architectural plans, financial reports, identification materials, and family letters. Many users had no reason to know the name of the man whose work made those pages possible. Such anonymity is common among the creators of foundational technologies. When an invention becomes reliable, affordable, and universal, attention moves from the machine to the work it enables. The most successful tools almost disappear into daily life. Yet every page still carries a trace of the original insight. Inside a modern laser printer, digital information becomes timed flashes of light. A beam sweeps across a photosensitive surface. Electrical charge guides microscopic toner particles. Heat binds the image to paper. The process takes place in seconds, but it represents the union of physics, optics, electronics, chemistry, mechanics, and computation. It began because one engineer refused to accept the boundary between a copier and a computer. Starkweather's story also reveals how strongly important ideas can be resisted. His proposal was not rejected because it violated the laws of physics. It was resisted because it did not fit the organization's existing expectations. Managers saw a copier business, while he saw a future in which computers would create complete visual documents. They evaluated a strange machine. He evaluated a new relationship between information and paper. Had he accepted the first decision, the laser printer might have emerged later from another laboratory. But Xerox would have lost the moment and the world would have waited. His persistence was not blind stubbornness. It rested on technical evidence. He built prototypes, solved defects, and demonstrated output. Each working page made the argument stronger. The cylindrical lens that corrected an expensive polygon error offers a perfect symbol for his method. Innovation does not always require a more costly or powerful component. Sometimes it requires viewing the problem from a different angle. A cheap lens can defeat an expensive obstacle when placed by someone who understands the path of light. A discarded copier can become the foundation of a new industry when examined by someone who refuses to see it only as a copier. A laboratory laser can become the pen of a computer when an engineer asks a question that others consider unnecessary. By giving digital work a professional physical form, the laser printer changed the role of the personal computer. Before high-quality printing, the computer could appear to be a machine for calculation and data processing. With graphical screens, page layout software, and laser printers, it became a publishing system. Writers could prepare manuscripts. Designers could arrange type and images. Businesses could create polished reports. Teachers could produce classroom materials. Small organizations could communicate with a visual quality once reserved for large publishers. The printed page became a bridge between electronic creation and the established world of paper. Even in an age of cloud storage, tablets, and electronic signatures, that bridge remains useful. Paper requires no battery, no compatible software, and no active display. It can be carried, marked, archived, signed, posted, folded, and read with the naked eye. Starkweather preserved paper's usefulness not by resisting computers, but by connecting it to them. His life, therefore, belongs to a larger history of inventors who merged technologies that other people keep in separate categories. He joined laser optics with xerography, digital data with physical documents, computer graphics with office equipment, and later color science with publishing and film. Across all of these fields, the central challenge was translation. How can invisible information become a reliable, visible result? How can one device understand what another device means? How can an abstract page become marks on paper without losing its structure? Starkweather answered those questions through machines that manipulated light. The next time a printer wakes, spins its internal motor, draws in a sheet, and delivers a warm page, the event will probably seem routine. But hidden inside that routine is a once unpopular vision. It carries the vision of a child dismantling broken radios in a Michigan basement, a physics student learning the laws of light, an optical engineer studying a troubled facsimile system, and an inventor staring at a copier drum while imagining a page that did not yet exist. Gary Starkweather did more than invent a faster printer. He gave the computer a precise and flexible way to write in the physical world. And with every beam that scans, every particle of toner that falls into place, and every digital idea that becomes a page, his invention continues to speak.